Greetings. My name is Devendra Das Sarma. I'm an Intel Senior Fellow, and I am the chair of the UCIe Consortium. Today, I will talk about Universal Chiplet Interconnect Express, UCIe for short, an on-package innovation slot for compute, memory, and storage applications. You can ask your questions on the Slack channel, and we will answer them. Here is the agenda for today. We'll talk about interconnects in compute landscape. Then we are going to delve into UCIe, an open interconnect for chiplets for the innovations in compute, memory, and storage applications. And we are going to then talk about final future directions and conclude. So we are living in this world of innovations. And what's really driving that innovation is the explosion of data, which is effectively enabling a revolution in the data-centric world. And here is a chart that shows how data is exploding. And the drivers are the usual suspects, cloud, 5G, sensors, automotive, IoT. Huge amounts of data is generated, and they all have very aggressive time to insight goals. And the challenges are with respect to how do you scale, right? Latency is important, bandwidth is important, capacity is important. So fundamentally, you have to move the data faster, store more data, process more data, and do everything basically seamlessly, efficiently, and securely. Here's the compute landscape, as you can see here on the right-hand side. This is a typical data center or cloud environment. You have a lot of servers which are put in the racks, and those servers are connected internally they're on a board, right, on a chassis kind of a thing. And there are multiple ones in a rack. There are multiple racks in a pod, huge number of pods in the data center. Everything that you see here that is outside of a node or outside of that server is connected through networking kind of interconnect, like Ethernet, InfiniBand, what have you. And these are the ones that scale is important here. Hundreds of thousands of these nodes are getting connected. So, they tend to run really fast. Latency is not that important. What's important is making sure that you deliver a lot of bandwidth and a fixed number of connections. Within the board, we have what is known as the latency sensitive load store interconnects. So these are the interconnects with load store semantics. So these are latency sensitive because you're connecting to memory. You might have a miss in your CPU and you're waiting for that data to be loaded into your cache. So latency is very, very critical there. They all have some kind of ordering semantics, and fundamentally you cannot lose transactions there. Very tightly coupled systems. These also move data very fast, and but not as fast as the other side. You have currently 32 gig in PAM4 in NRZ, moving to 64 gig with PAM4 with PCI Express Gen 6. PCI Express typically forms the fundamental interconnect of all of these. You got hundreds of lanes in a given node, and power is very important as a result. Cost is important. Area in the silicon is important because of the number of nodes. Backward compatibility is important. Of course, latency is important. And typically, these are on board. And how important is the latency? For example, the phi latency from pipe to the pin and back is more or less flat over these last few generations of the evolution of these interconnects. And they are less than 10 nanoseconds, right? So contrast that with 100 plus nanoseconds that you will have on a networking kind of an infrastructure. Now, today I'll talk about the other aspect of it. So once you look within the node, a node consists of several packages. Within that, you might have one or multiple dies. And how are the dies connected together? I will talk about that. So those are fundamentally also load store. Today, they are proprietary, and UCIe is going to move them to a standard form of interconnect, the same way we have done board level interconnects on standardized interfaces. So UCIe speeds are typically 4 to 32 gig, single-ended NRZ, very, very, very simple circuits. Connectivity is 2D, 2.5D, moving towards 3D interconnects. Thousands of lanes. If the previous one was hundreds of lanes, these are thousands, tens of thousands of lanes that you're going to have. So as a result, the power efficiency, it needs to be ultra low power, ultra low latency, and very, very high bandwidth density. And the latency is even more critical in these interconnects, less than 2 nanoseconds, an order of magnitude better latency. And we will see how that manifests itself. So these are also going to be load store. So what you can see is that the load store interconnects are there everywhere from within the die to with UCIe, they are going to be at the package level. We already have load store interconnect with at the board level with PCI Express, CXL, and also even the CPU to CPU proprietary links, like, for example, Intel has its UPI, others have their own protocol. And CXL is extending, from even the node level to the rack level with CXL2, CXL3 pooling and all of those. So load store is going all the way from the die to potentially the rack level, and from the rack, from the node level to rack at the rack level and beyond, it's all networking and fabric kind of interfaces. So now let's look into the off-package load store interconnects, which are PCI Express and CXL. PCI Express, very well established interface, more than 2 decades old, 950 plus member companies. There what happens is that it's a non-coherent interconnect. Although it's load store, it is non-coherent. So the memory that is connected on the other side to the CPU that has got caching semantics, you can cache that memory, but you cannot do that on a PCIe device. And by the same token, memory that is attached to a PCI Express device, you cannot cache it in the system side on the CPUs. And different ordering rules, and the CPUs typically handle that, and that really works well. That's the load store interconnect using producer-consumer ordering semantics that exists in PCI Express. Works really well, especially in the storage segment, right? It works well. Networking segment works well. GPUs has worked well, has really worked well. Now with CXL, which we have about 250 member companies, what we did was that we basically kept everything that PCI Express has. We have the same PHY, we have the same infrastructure, but we have the same DMA semantics, the non-coherent DMA semantics that PCI Express has. But on top of that, in addition to that, we added coherency semantics. So that is the CXL.cache, and memory semantics, so that a memory that is attached to a device, CXL device, can be mapped to the coherent system memory. So that's the CXL.mem. So now what happens is that with these, now you can use the PCIe slots to attach, for example, a CXL device and have memory that's mapped to the system memory, get more memory bandwidth. You can attach a GPU that can cache the contents that is there in the DRAM or somewhere else, which is mapped to the system memory. So all of these are possible now, in addition to the bulk move that we were able to do with non-coherent with PCI Express. PCI Express and CXL, these are very, very successful industry standards. They're multi-generational. PCI Express is currently in the 7th generation. CXL is past the 3rd generation now. They're backwards compatible. There are lots of IPs available. There are lots of tools available for people to develop. Very well-established compliance program. Plug-and-play guarantees are there, right? Because of all of these. So when we looked into on-package interconnect, we said that we need to leverage those same learnings that we have from PCI Express and CXL over the decades, and use that for standardization and also the load store usages. And fundamentally, we need to be able to move things seamlessly from the node level to the package level to the die level. So this is a picture that if you see that on the left, you have node, which is basically a server. It's a 2 CPU socket server. You can see that 2 CPUs are connected through cache coherent proprietary link on PCI PHY. Typically, you got DRAMs connected through DDR-based DRAMs that are there connected to the CPU, and you got some number of slots, which can be either a PCI Express device or a CXL device. They're plug and play. So that's the PCI Express side of things are full plug and play. You can have any mix of devices. You can get them from any supplier and plug them in, and it will work. When we go to the board level, we have similar things that exist at the from the board level to the package level, things that are successful at the board level. We want to make sure that the same kind of plug and play works at the package level. So here, for example, I can have some CPUs, I can have some accelerator, I can have a tile for IO, on which out of which we will have PCI Express, CXL, all of those come out. We can have some on-package memory. So things that were there at the board level, I should be able to do it plug and play way in the package level. And that sometimes makes sense because then you are going to get really dense amount of compute and you can do a lot more things. And we'll see how that's, because you are at the package level, you can get a lot of things done. And of course, you should be able to move to on-die integration, and the same IPs, we need to be able to move them seamlessly between at the board level to the package level to the die level. And also sometimes from the die, we should be able to partition things and move them to multiple dies at the package level. And this enables us to basically reuse components. We get a better user experience, things will just work. We get the economies of scale, we get time to market advantage, all of those things. So that's the vision for us. Things that have been successful at the board level, full plug and play with PCI Express CXL, we want to mimic that at the package level with UCIe. Now let's talk about UCIe. And there are 4 founding principles based on the learnings of those successful standards, PCI Express and CXL. Personally, have been involved in it from the very beginning of PCI Express and CXL. One is open ecosystem, right? Open standards, open ecosystems that drives innovation in the industry. We of course need to deliver the best power, the best performance, the best cost metrics that can be thought of. We also need to be ubiquitous. We need to meet the needs of multiple segments of the market, otherwise you become a niche. And of course, you need to continuously innovate with backward compatibility when it is appropriate. So these are the founding principles of UCIe. So let's start with with a quote from Gordon Moore, who recently passed away. He was an institution by himself. So he's very well known for predicting Moore's law in his seminal 1965 paper. In the same paper, he predicted the day of reckoning, where he said that it might prove to be economical to build large systems out of smaller functions that are separately packaged and interconnected. And we are already there. We already are seeing, mainstream CPUs, GPUs, you name it, different types of SoCs being built out of smaller dies and packaged together. So it's out there in volume, right? It's there from us, Intel, from our competitors. Everybody is doing it, and primarily the reason for that is we are all up against the reticle limit. The demand for, in our case, compute is insatiable. So you need to, for example, put more and more cores, and you're up against the reticle limit. So you basically do a lot of smaller dies, stitch them together on the package, and off you go, right? You have an SoC that is fundamentally at the package level. So that's something that everybody is doing today. Now, our vision is that we need to, just like, so the moral equivalent of that is like CPU to CPU scale up connectivity using proprietary interconnect, but they run today on PCIe 5. So we want to definitely keep that usage model, but we want to at least make sure that they run on the UCIe 5. But in addition to that, we want to enable this notion of heterogeneous compute. So for example, as you see in the picture here, you've got a sea of cores. You are going to have some number of chiplets that are going to be accelerators, networking, all of those things. You are going to have memory. So they can all be connected together using the same standard interface. And as a result, with this, not only do you still enable the scale-up solution of constructing, system on a chip like people are doing today, but in addition to that, you can now have different types of components that you can pull in. And this helps us with reducing the time to the solution. Portfolio cost will be lower because you can deploy optimal process technologies for different things. Like memory, you can do it using a memory process node that's suited for memory. Smaller dies yield better. IP porting cost, which is exploding. Even if you change nothing, the IP porting cost across the more advanced geometries are going up and up in terms of their cost. So it reduces those IP porting costs because those IPs that don't change, you put in a chiplet and you continue to reuse that chiplet. It lowers your overall SKU cost, but most importantly, it enables us to offer bespoke solutions. So you can do different solutions for different people, and it scales innovation. So the goal is to align the industry around an open platform to enable these chiplet-based solutions. Now, what are the key metrics that that are important, and what dictates the adoption criteria? There are two sets of things, right? One of them is, of course, the key metrics. The other one is the business conditions, right? That's going to make sure that a standard becomes successful. And again, these are based on our experience from PCI Express, CXL, and so on and so forth. So in this context, the key metrics are bandwidth density, linear area density, energy efficiency, because not only the peak power consumption, but also we want to make sure that our energy consumption scales with the bandwidth usage. By that, what I mean is, if I consume 10% of the peak bandwidth, ideally I should consume 10% of the power that I had consumed at the peak bandwidth. For that, not only do you need power savings, but also you need to get into and out of those low power states very quickly. So low power entry and exit times, latency is super critical, channel reach is important, reliability is extremely important, as is availability, and of course, cost, right? So you need to make sure that we offer the right solutions for the right applications. Now, on the other side, we need to make sure that there is interoperability. Otherwise, you're not going to have a healthy ecosystem. So you need to define a full stack. You need to do plug and play with existing software, different usages, different segments. You want to make sure that you're scalable enough to span the entire compute continuum. Portability across technologies, whether it is process node, different packaging technologies, you need to think of the holistically, what's the power delivery solution, cooling solution, repair strategy, debug strategy. Most importantly, do you have the broad industry support and an open ecosystems? And these are, again, the learnings from past standards efforts. And UCIe has been architected and specified ground up to deliver the best KPIs while meeting this wide adoption criteria. So now, in order to jumpstart UCIe, we Intel donated the 1.0 specification, and now it belongs to the UCIe consortium, and it's a fully defined specification. The consortium is working on advancing the technology forward, defines the physical layer, the protocol layer. From a protocol layer perspective, we have mapped the CXL protocol, the PCI Express protocol, and also we have provision for what we call streaming protocols. And under streaming, you can map other protocols, like the ARM folks are interested in mapping the CHI ARM protocol onto UCIe using the streaming protocol. So those are all supported. It's a well-defined specification, and this is basically the extent of the protocol, right? Everything from the die-to-die adapter, we define the interfaces here, and the physical layer along with the channel model, everything else, including the compliance. It's a full spec. We support both standard packaging and advanced packaging. So the picture here on the top left is a standard package. So these are your standard bump pitches, 100 to 130 microns is what we define it. Same as what you will have on an external package. These are cost effective. You can go longer distance. So you get a lot of possibilities in terms of where to place what on the package and connect them. The other type is the much more denser one, and that's known as advanced packaging. These are very power efficient because the distance is really short, less than 2 millimeters, very high bandwidth density. And the basic idea is that the dies can be manufactured anywhere in any fab house, designed by anybody, and you can mix and match and package them somewhere else, right? So this is just like what you did at the board level, where you can make the, you can get somebody's CPU, you can get somebody else's GPU, you can get the DIMMs from somebody else, design your board, them together, it just works, right? So on the advanced package, I've given examples of 3 advanced packages. And again, 3 is not meant to be everything. This is just some sample examples. The topmost one there is Silicon Bridge EMIB from Intel. The next one, the one in the middle, is CoWoS from TSMC. And the last one in this example is Focus, which is from ASC. And your dies can be done by anybody. For advanced package, we define the bump pitch between 25 to 55 microns. So these dies can, as long as you are within that range, you can go and assemble them using any of these advanced processing technologies. So one UCIe spec covers the entire spectrum here, from standard packaging to the advanced packaging. Now let's talk about the usage model of UCIe. So clearly we want this to be SoC at the package level. So, you have the example that you see here is you got some processor nodes at the bottom, you got some accelerators, you got some memory, you got some analog RF chiplets, you got some modem chiplets, some optical chiplets, all of these things. And then you got memory and IO controllers. So some of them are like your processors, you can keep changing very frequently. The rest of them can be constant, right? And they are all connected using UCIe. So, this is really the mix and match, right? You can also choose to have maybe 2 processors and 4 different types of accelerators. You can have mix and match of the accelerator. So homogeneous chiplets as well as heterogeneous chiplets and mix and match from different suppliers. And this can be across the entire spectrum, right? Handheld, client, server, automotive, workstation, communications, all of those things, similar to what we have today, PCI Express or CXL at the board level. The other usage model that we have is off-package connectivity with retimers, UCIe-based retimers. So, if you look at the top, the rightmost picture here, the bottommost, which shows the CPU package, you have, for example, the CPU that is, you got a bunch of CPU chiplets connected with on-package memory, some memory and IO chiplet. And then you got UCIe retimer through which you have optical connectivity coming up. On the one above that, you see a CXL-based switch, which consists of 2 switch dies. So that way you get larger number of fan-out switches of CXL. And you got UCIe retimer optical chiplet on the top. The 2 switch dies are connected using UCIe, running the switch's internal proprietary protocol in the streaming mode. Now what happens is that at the bottom of that, you connect to a whole lot of pool of shared memory, a pool of accelerators. So if you look at the picture on the middle, the basic idea is that, these different drawers or different trays where you have compute node, you are going to escape the green colored lines or maybe the co-packaged optics, the optical connections that are going. So you can have a compute drawer, for example, talking to a switch that fans out to a whole lot of pooled and shared memory and accelerators on some other drawer, maybe in a different rack, and access those resources as if they were next to you. So UCIe enables you to go and make those accesses possible. So let's take a look into the characteristics and key metrics of UCIe 1.0. We support 4, 8, 12, 16, 24, 32 gigabit transfers per second data rate. So if you support a given data rate, you have to support all the lower data rates. That ensures that you can do your design to whatever is the need of your particular chiplet, and you don't have to worry about interoperability with somebody else. You can design to 16 gig, you will interoperate with somebody that has designed to, let's say, 8 gig, or somebody who has designed to 12 gig or 32 gig. So that guarantees interoperability. The width per cluster is given here, 16 for standard, 64 for advanced. So you can have up to 4 clusters. So for example, each cluster here, a standard package cluster is equal to a by 16 PCIe Gen 5. A 64 lane cluster running at 32 gig is equivalent to a PCIe Gen 7 by 16. We support a wide range of bump pitches for interoperability. Standard is 100 to 130. Advanced is 25 to 55. Channel reach is 25 up to 25 millimeter for standard package, gives you a lot of flexibility in terms of placing the chiplets. And advanced package needs to be closer, less than 2 millimeter. What we see here is the key metrics, the bandwidth density, both linear as well as area-wise, the density. We are pretty much bump limited. So you are going to see a set of ranges that are given over here. So for example, those are proportionate to the bandwidth with which you are running. So for example, in advanced package, the bandwidth density is 188 gigabytes per second per square millimeter if you run at 4 gig. If you run at 8 gig, it will be 376 gigabytes per second per square millimeter. If you run at 32 gig, then you are at 1350 gigabytes per second per square millimeter. And these are done in advanced packaging for 45 microns. So if your bump pitch is 25 micron in advanced packaging, then you're going to get more than 3x the number. So contrast these numbers with, off-package link like PCI Express or CXL, there you get about 10 gigabytes per second per square millimeter. So 2 to 3 orders of magnitude more bandwidth density, which is expected because these are really short channels. Power efficiency wise, 0.5 picojoule per bit, 0.25 picojoule per bit. And importantly, you can get into and out of low power state in 0.5 to 1 nanosecond and save 85%. So practically, if you don't have anything to send, every clock cycle, you can turn that off and save 85% of power. Now, from an external link point of view, the power efficiency is 5 to 10 picojoule per bit. So you're going to get an order of magnitude better power saving. But most importantly, the power consumption for bandwidth usage is much better here, because you can get into those low power states in and out much quickly, because external links are more complex circuitry. You need microseconds in order to get into and out of it. So you pretty much are going to get a power consumption that's proportionate to bandwidth usage, which is very important in these on-package links. Latency is less than 2 nanoseconds, and again, on order of magnitude better. And reliability is pretty good. So we measure reliability in FIT, which is failure in time, how many failures we get in a billion hours, and that's expected to be less than 10 to the power minus 10. So very compelling characteristics, and we expect this will serve the needs of the compute segment for the next 5 to 6 years. So UCIe incorporation is incorporated. We have lots of working groups running, basically evolving the technology forward. 1.0 is not the end of the journey; it is the start of the journey. And 110 plus member companies. So lots of excitement in the industry, and across different segments, we expect a lot of usages. For example, in the storage segment, you can imagine your SoCs being built out of chiplets. Where you have some chiplet that does encryption, decryption, some that does near memory compute, some that's taking care of the media. So you can mix and match all of those and really innovate with this chiplet technology. So join us if you have really not done so. It's going to be an exciting journey for the next few decades. And please do rate the session, and we'll take the questions. Thank you all very much.